This is topic 11 in Unit 1, Assessing Normality. In this topic, we are going to discuss formal ways to determine if data comes from a population that is normally distributed. So far, we've talked about a few things regarding normally distributed data. The first was after we made a histogram, we looked at the shape that occurred as we drew a line over top of the bars to get an idea as to whether or not the data is bell-shaped. Secondly, we discussed the empirical rule, which stated that 68% of the data will fall within one standard deviation from the mean, about 95% of the data will fall within two standard deviations from the mean, and about 99.7% of the data will fall within three standard deviations from the mean if we've decided that our data is normally distributed. What we really want to do, however, is come up with a formal way to make a decision as to whether or not data comes from a population that is normally distributed. And in statistics, we do this by performing a statistical test. There are three different steps to the process of checking for normality. The first one is to make a histogram, which we've already done and discussed. And the second two are going to be new to us for this topic, and they are make a normal probability plot and perform the Shapiro-Wilk test for normality. This is our first formal statistical test, and we will be doing this a slightly informal way. And then in Unit 4, we will come back and look at all of the formal pieces that we need to complete this test entirely. There are also other types of tests for normality. Anderson-Darling is a popular one, and there are other ones besides this one. Shapiro-Wilk and Anderson-Darling are the ones that I have used the most myself. So rehashing histograms. We've already discussed how to make a histogram. We will get into how to make a histogram in Stata starting with this topic. And one thing that you want to consider when you are evaluating your data and trying to make, informal decisions about them before you've run a test is your sample size. So I know we've mentioned that the word small sample size are dangerous, but that's one thing that you do want to take into account. So if the sample size is 20 and our population is very large, so it's, people in the United States or maybe even people at Casper College, if the shape of the histogram is bell-shaped like that, it's still good evidence that our population is normally distributed, but since our sample size is on the smaller end, we would want to have more pieces to consider for normality. This other slide, however, let's suppose the same histogram was the result of a sample size of 200. Even though the sample size is larger, we're not 100% certain until we've run a test, and even then we're not completely certain as at least 100%. This is definitely better evidence that our population is normally distributed. So the idea is that the closer and closer you get to a census, the more confident you will be. So in general, the bigger your sample size, the more confident you'll be that you're truly capturing your population. But again, as long as you select your sample well, you still may be able to have a really good representative sample that is a smaller sample size. So the next thing that we're going to make in order to assess normality is a normal probability plot. And this is going to be a new graph for us. And this is also one that we are not going to go into the technical details of creating a normal probability plot. If you are interested in its creation, please send me an email and I can send you to a link that will have a nice step-by-step way of how this is made. So it's a technique for assessing whether or not data comes from a population that is normally distributed. And there are going to be three general options that we're going to have when we're interpreting the graph. The first one is that if you have mostly a straight line and the data points fall along that straight line, then we have pretty good evidence that the population is probably normally distributed. If the data points fall on the line and somewhat off of it, then we may not be sure based on looking at just the plot alone. And in general, until we've done a test, we don't really feel certain or confident at all. We just like to get an idea of what to expect. And then lastly, If the plots, the points fall on the line, not much at all, they're scattered all over the place and they don't really follow the line very much, then that's a pretty good idea that your data is not normally distributed. So if we look at an example of each one of these cases, we have the leftmost graph where most of the points fall in the line pretty nicely. This is a pretty clean probability plot. So if I were to look at this graph, I would probably want to, I would think that there is a good case that the data comes from a normally distributed population. For the second graph here, we have some of the values falling along this line. So we're looking to see how these dots fall along the red line here. They're kind of on the line. They go a little bit below here. They dip a little low, and they have some strays towards the end here. If I were to look at this, I would actually not be certain if our normality test would pass or not. This one actually doesn't look too bad. So I would still be uncertain, and again, until we run the formal test, the Shapiro-Wilk test, we don't necessarily make a decision. This last graph here is definitely pretty gross. There's not really much of a straight line at all. It's very curve-shaped. This is a good idea that it's probably not normally distributed population. So again, sometimes it's up to your judgment when you're just eyeballing these graphs. And so that's why it's really important to explain your reasoning on any question that involves interpreting a probability plot. And the question will always ask you for that, but if you make a good case, this one maybe could go either way, depending on how you interpret it. And given that there's different interpretations, this is why we don't want to leave any of these decisions up to our eyeballs. So we actually want to run a formal test. And so the Shapiro-Wilk test for normality is going to be our final step in checking normality. So when you perform the Shapiro-Wilk test, you're going to get what's called a p-value. In Unit 4, we're going to talk in detail about what a p-value is and exactly how it's calculated. But for right now, we're just going to get exposed to it and understand how to interpret this p-value. So this is actually a good introduction, and when we get to Unit 4, it will really help having a little bit of exposure to this. So there's two cases with a p-value that we're going to break this down into. First of all, a p-value is a probability. So you can't have a probability of something happening less than 0% or more than 100%. So this corresponds to probability values of 0 and 1. So if the p-value for the Shapiro-Wilk test is between 0 and 0.05, so on your number line here, that's going to be pretty close to 0, pretty small values. If you have a p-value that falls in between this range, there is evidence to against data coming from a population that is normally distributed. If your p-value is between 0.05 and 1, which is the whole rest of this number line here, then there is evidence in favor that the data comes from a normally distributed population. Let's look at a few examples. Here's a slide that has how we're going to be doing all the rest of the steps in Stata. I am going to show how I'm getting these graphs and performing these tests. So this is more of just a reference for you. So the first example, the following data represents the number of pups in wolf dens. This is real data that was collected. I don't have a ton of information about their sampling method, but this would be really tough because we don't know where all of the wolf dens are. So maybe they were able to locate a number of wolf dens and hopefully they randomly selected some of them. So perform a complete normality assessment. So in this case, a complete normality assessment refers to those three pieces that we saw earlier in the slide, which is a histogram, a probability plot, and the Shapiro-Wilk test. So I already have my data entered here, and it's going to look a little funky, and that's okay because I sorted my right column. So I just put my first example in the leftmost column, and I wouldn't worry about putting this data in yet. I just wanted to have it in for the second example. So from now on, we want to make all of our selections from this command window. So this is the command window because it's the screen that has this command box down here, which we did have to type in once in a previous section. So the first step is to go to graphics and then select histogram. We're going to make a histogram of our wolf pup data first. So I want to select my variable. There's a lot of options on this menu. I try to set this up as much as possible, but usually I have to go back in pretty frequently and make some changes to make my graph look how I would like. So this is going to be discrete data because you can't have, 5.5 pups in the wolf den. So we're going to select the discrete box. And then over here, it defaults to density. And what you want to do is check this frequency box. You have a lot of other choices up here. What I would recommend is, and we're eventually going to adjust these bins too as well, which we'll talk about with the next example. So I want my x-axis to have a label, and we'll make this be number of pups in wolf dens. It is very, very important that you label your graphs properly and clearly because you want another person to be able to look at your graph and read and understand it as easily as possible. And so the more labels that you leave out, the more questions that they'll have for you about reading your graph, and the less your graph would be effective. I think y-axis is going to have frequency, and that's okay. You can also adjust where your tick marks are shown for your x-axis and your y-axis, and this is something that you'll have to do in an upcoming lab activity. So when you hit OK, a window is going to pop open with your graph in it. So I think this is a pretty decent looking graph. So this is the number with 3. So there's 2 dens that had 3 pups. There was 2 dens that had 4 pups, and so on. So I like the way that this graph looks because I can look at it and easily understand what the data is that it's describing. So this graph is reflected here in my solutions. So you can window this down. I'm going to close out of it because I won't need it anymore. The next graph that we want to make is a probability plot. And so this is again going to be under graphics. There's actually a number of places that you can find these graphs in these drop-down menus. I'm typically going to use the same location every time for creating them. So we want distributional graphs because we want to see about our distribution of our data. And we're going to select a normal probability plot standardized. So the good news is that when you select this, the only thing that you need to do is select your new variable. You don't need to modify anything at all. As a matter of fact, we want you to leave the labels alone completely. Because since we're not talking about how these are constructed, it's not really easy to understand what the labels actually should be. So here's the normal probability plot, which we will interpret in just a few minutes. And then lastly, to get to the Shapiro-Wilk test, now you're going to go to Statistics, Summaries, Tables, and Tests, Distributional Plots and Tests, and here you're going to see there's that graph again. And then you want to go down and select the Shapiro-Wilk normality test. And again, once you do this, the only thing that you'll need to do is select your variable. So I don't want both of those, I just want one. And then hit OK. So this whole window I typically will include as my output. This is the p-value that we were talking about. So that's the p-value that is the output of the Shapiro-Wilk test. So now let's discuss these 3 normality assessment components. The histogram is not perfectly bell-shaped, but I think it looks pretty good. It's definitely not completely unbell-shaped, but again, this is why we need a formal test, because everybody can interpret these graphs differently. There's not a single scientific way to interpret a graph. Not only that is that you can make a histogram with 10 different scales on the bottom, which we'll see in a little bit here. I think that this histogram suggests that we probably will end up having normally distributed population, but again, until we run the test, we don't make that decision for sure. So secondly, this probability plot is a little bit different. We won't typically be looking at discrete data for this, but it definitely makes for understanding of this picture. So when the probability plot is made, it orders the values from low to high, and it figures out what they should be if the data is normally distributed. So this is the one where we have our mode here of 5 pups in the wolf den. So this here is pretty untypical. The data isn't falling right on the line, but it's still not really that bad. Again, since our sample size is small, it's going to be easier to say that the population is normally distributed, unless it's really wild. So again, I kind of think this suggests that the population may or may not be normally distributed, and just from experience, I would expect that it would be normally distributed. And lastly, our Shapiro-Wilk test. The p-value again is this right here. So p-value prob, it's the only p that's going to occur across the top. So this is 0.67175. This is a pretty high p-value. Real data is normally distributed extremely often, but even then the p-values are sometimes pretty close to 0.05. But in this case, we're way above 0.05. We're more than halfway towards 1. So formal conclusion is that the data suggests that the population is normally distributed, since this p-value is between 0.05 and 1. So one thing that you may have noticed is that we're never definitively making a decision. And this seems kind of lame, but the truth is that unless we've come up with a census, we have no idea at all whether the data is normally distributed or not. So this is an alternative to having no information whatsoever. I would be pretty confident, however, that the number of pups in the wolf den would be normally distributed. So the next example, this is an actual sample that I performed. It's a number of Facebook friends on a person's Facebook account. Perform a complete normality assessment, and then determine if there are any outliers. I would pause the slide right here and make sure that you can go through all this data steps, and then search back into the previous section to remind yourself of how we determine what an outlier is. Okay, so these are the 3 components that you should come up with for the normality assessment. You should have a histogram. I'm going to show after this slide, before we talk about outliers, what the bins thing is all about. The initial histogram that pops up from Stata, there's nothing wrong with that one. I just think that there should be a few more classes, and we'll talk about that. The QQ, or the probability plot, isn't looking that good. So between the two of these, I would say that we do not have evidence of a normally distributed population. This is falling way low, and then we hop up towards the end. This usually happens, so this behavior at the end is kind of bad. And then the say-all end-all is our p-value right here of 0.0008, which is less than 0.05 for sure. So because of this, we say that there is evidence to suggest that the population is not normally distributed. So I think this would probably be pretty true of most people's Facebook friends, because there's probably a lot of different populations of people on Facebook as far as their friending habits. So for example, some people only friend people that they know personally, whereas other people may friend or follow people that are celebrities, or they have they friend people that are friends of friends that they have a lot of mutual friends with. So there's a lot of different considerations to take into account, and it really doesn't surprise me that this data does not appear to be normally distributed. So let's take a minute to look at the histogram creation here. So I have my data in already, and we're going to go to Graphics, Histogram. So we don't want number of pups anymore. I have Facebook friends in here. So Facebook friends is also discrete, technically. If you had selected continuous for this one, it wouldn't hurt at all. But if it is discrete, you definitely should specify. If it's not, I would select continuous as much as possible. So frequency is okay here. We're not necessarily comparing this at this time. Percent would be stronger. So it doesn't specify what kind of histogram to make, and this is because we only care about the shape. So I'm going to label the bottom axis. And then I'm going to go back to this main category. In bins, what the bins are is it's the number of classes that you're going to have. So they're called, I'd say 50-50 bins or classes. So I originally, we need to select continuous for this one. So that's a good point to make. If you have discrete data, it's not going to give you the option to really customize your graph. So even though this is technically discrete, we want the flexibility of the continuous option. So let's do the default. Okay, so this is the default what that would look like. And so that's definitely not what we want a histogram to behave like. Sorry, my window disappeared here. So that's the first indication that something kind of funky is happening. So I'm going to click the continuous, and this is the graph that is resulting. So this definitely looks better. When you are selecting discrete, it basically has each number of possibilities. So every single Facebook friend from 0 to 2000 has it be a class width of 1. So the continuous graph is looking better. But I also want these broken down a little bit more. So I'm going to go in and make this again, and these graphs are just kind of, they didn't go away if you don't X them out. They just compile along the bottom. I'm going to select this one, which is what I would assume that my original graph was made from, was 10 bins. So what this does is it takes the total range and it splits it into 10 classes instead of 3, which is what we had originally. And you can change this as much as you want. So if you want this to be 20, you could do that as well. And this is one reason why histograms are not something that I'll ever look at alone, because you can make 50 different histograms and every single one of them could look different if you change your classes along the bottom. So if you have more questions about setting up some of these things in Stata, there is a video that has the general how-tos of Stata that go a little bit beyond what is included in the videos. So check those out. That will be under the main category. Underneath the syllabus and the Stata instructions, there'll be a section for Stata videos. So we have one more question here, and that is, are there any outliers? So what we need to do for this is what we did in the previous section, which is get the descriptive statistics. And you have to select the get more descriptive statistics because you want to have the 5-number summary, which is the minimum, quartile 1, quartile 2, quartile 3, and then the maximum. So the reason why I always select the smallest and the largest from the right column is that these don't always have to be exactly the same. So the smallest number that happens in the 1% category is the one you want to select over here. And the largest one in the 99% category is what you want to use for your maximum. Or you can just look at your data set. So the outliers are determined based on the IQR and the quartiles. So the IQR is Q3 minus Q1. And in this case, that's 644.5 minus 184, which will be 460.5. The cutoff for the upper number is Q3 plus 1.5 times the IQR. So basically we take the distance between the first and the third quartile, and then we give it just a little bit more room, so 1.5 that, to say, hey, anything outside this is pretty far out there, and that would be something we consider an outlier. So the upper number that we get here is 1,335.25. Anything above this number is going to be considered an outlier. For the lower cutoff, we have Q1 minus 1.5 times the IQR, and this ends up being a negative number, so there's no possible way that we can have an outlier on the low end is what this is saying. So even though this isn't a number to obtain, negative 506.75 Facebook friends, we still report it as is because we're not saying it happens, we're just using it as a way to describe where we are describing our outliers. So I'm going to show how I got this, as well as how I sorted through my list and decided that 1,811 was an outlier. So I would use the command window for every drop-down from now on. Previously, you did not have to do that because we just needed basic descriptive statistics, but now we want to be able to get everything we need as we need it. So statistics is where we're going to go to get anything that is calculated, and we want descriptive statistics and then summary statistics. So you can just follow the menus. It's usually self-explanatory. If worst comes to worst, you can click around a little bit. I think the labels are pretty decent at describing what type of actions you can make once you open those menus. So descriptive statistics, I want my Facebook friends, and I want it to display the additional statistics. So this is the same menu that had came up previously when we were in the data entry menu, but this is going to give us all these options here are going to be everything that we'll need to do within Stata. So when you hit OK, you're going to get this menu that I have here. And so this is just how I got the descriptive statistics that's on this last slide. And then lastly, in the data entry window, I didn't want to have to sort through this one by one. So an option that you have is go to Data and then Sort. And you can select a variable that you want to sort on, which in this case is friends. And then you can have it be ascending or descending. I just, want it to be in order somehow. And then hit OK. So this was already ordered, that's why nothing changed. And it also connected to the values that was in the previous cell. This does not affect anything that has happened here at all. Stata treats a missing number by placing a dot there and then completely ignoring it when you do any analysis. So if you do have a bunch of dots at the end of a data set like this, nothing bad will happen. It's going to completely ignore it. So anything outside of negative 506 on the low end is an outlier, which we can't have. And then anything above 1,335.25 on this high end is an outlier. So this one is good, but then this one is a little bit too far out. So 1,811 is an outlier. I would definitely go through and practice these questions on your own. There will be a practice that will go up before the exam. Please feel free to email me if you have any questions.